In this lesson, we're going to look at another measure of spread for one variable statistics. This one is called, well, actually two, but they're tied together. Standard deviation and variance, they're pretty much very similar. And they both, again, will tell us how spread out the data in a data set are. Again, to recap some things we've talked about before, we can find the measure of central tendency of a data set. In other words, what the middle is. We got the mean, the median, the mode. And we've also talked about ways that data can be spread out. We looked at box and whisker plots to see how things spread out. The range, percentiles gives us an idea. But this one we're going to focus on today is the gold standard of how we measure spread, standard deviation. And then we're going to see how that ties into something called a Z-score, which we're going to come back and look at again later in this course as well. So let's look at what standard deviation and variance are to begin with. So the variance and standard deviation of a data set allow you to determine how close the values in a distribution are to the middle of the distribution. And in this case, we're going to use the mean as the as what we mean by the middle in this case. You can calculate the variance and the standard deviation of a data set using the following computational formulas. So you see four formulas on the screen here. They're really slight variations of the exact same thing. The two top ones are just the difference between population and sample. We've seen before that we can talk about a population mean and a sample mean in previous lessons. We're going to also talk about the slight difference between population variance and standard deviation compared to sample variance and standard deviation. So let's start with the population variance, and then we'll just see how the other ones are all related to it. So population variance, first of all, we have another new letter variable that stands for it. This here is called sigma. This is a lowercase sigma. We've seen, you may have heard me talk about sigma before. This is also called sigma, but this one is a lowercase sigma, if I'm not mistaken. I always have to hesitate for a second because I'm not the best on my Greek alphabet. Anyway, let's go with lowercase sigma, and if I'm wrong, then we can fix that another time. Anyway, so sigma squared is equal to the sum of, remember this uppercase one, this one right here, definitely is sigma, and it means add together everything that comes after it. So it's saying add up all the x squareds, and x is just the variable, that the x stands for all the different data pieces, and again, we'll go through an example of this. All the different data pieces minus n, which is the size of the population, uppercase N we've seen is the size of the population, and times mu squared. Remember, this is pronounced mu, and that is just the symbol we use to represent the average of a population. So this here, this whole thing together means the sum of each piece of data squared. So if I have a list of numbers, I would square each number and then add them together. That's what this is telling me to do. And we know what all the other ones mean from before. Compare that to the one beside it, which is the variance for sample. It means the same thing. Variance is given as s squared. We use the s for standard deviation, but we're going to see that variance is just standard deviation squared, so variance is s squared. It's still made up of just all the different pieces of data in the sample squared as opposed to the population now, but it's still just a list of numbers squared, minus n, which is the number of pieces of data in the sample, so it's lowercase n to indicate that it's a sample, times x bar squared. And remember, x bar was just the average of all the sample pieces. So again, exact same thing, just different variables. The only, other than the variables being different, the only thing that's different, that is actually different, is that our denominator now has n minus 1. And we'll get to that in a minute as to why it's a minus 1 here. So for population, we just divide it by n. For a sample, we divide it by n minus 1. So exact same formulas, almost different variables. And then when we look at standard deviation, just below it, we see the exact same formulas again. The only thing that's been added now is we've taken the square root in each case. So what we can take away from this is that the relationship between variance and standard deviation is just that if I've got the variance and I want to get the standard deviation, I take the square root of the variance. If I had the standard deviation and I wanted to get the variance, I would square the standard deviation. Again, both of these are measures of how spread out data is. Now, as to why there's an n minus 1 on the bottom, that's explained in the next sentence below. Samples rarely contain extreme values when compared to entire populations. As a result, the variance and the standard deviation are less than they would be expected. Because they don't have those extreme values, the numbers are maybe a little bit too low. So that's why the formula uses n minus 1 in the denominator. By making the denominator a little bit smaller, it's going to make the overall number, when you do the calculation, slightly bigger. And so that's really a compensation. So you just have to, really what you have to do is you just have to pay attention to a question, decide whether we're dealing with the population, all of something, or a sample taken from a population, and then you can decide whether you're going to use n or n minus 1 in the appropriate formula. All right, it's possible to calculate standard deviation and variance with certain scientific calculators, almost all scientific calculators, in fact. You can look up how to do this online or using the instructions. It won't be covered in this class because there's many different ways it can be done. Having said that, I will go through just to show you what I mean, I'm going to give you a quick little look at my calculator so that you can get an idea of what I'm talking about. So let me just set this up so I can show you. I'm just going to turn my camera on for a second. Oh, there's my guitar. When I'm done my lesson today, I'm going to sing you guys a folk song. JK, don't worry, I won't. All right, so here is my calculator, and mine is the Sharp EL503W. And if you look at the right side of the calculator, from the equal sign up, you'll see some symbols. We've already seen the second function. You'll see above the bracket here, you'll see x bar, you'll see n, you'll see sx, and sigma x, those two symbols we just talked about before, so as in standard deviation, and, well, for a sample, standard deviation for a population. You'll see sigma x as in adding up a bunch of numbers. You'll see sigma x squared, things that are all familiar. Above them, you'll see data below that store button. So again, not every calculator is the same, although a lot of them are similar. For mine, this is how I would do it. If I turn on the stat mode, if you look at the screen, it doesn't say anything on it right now, but if I press second and then this button, it turns on stat. You can now see it says stat just above the 0 on my screen. So just to give a really quick, simple example of how this works, let's imagine I wanted to work with a data set that was made up of 5 numbers. The 5 numbers are 10, 20, 30, 40, and 50. In my calculator, I'd enter it like this. I'd type in the number. So I've turned on the stat function, first of all. I can turn that off and on, by the way. So I can go stat. So you can see that stat thing is appearing and disappearing on my calculator. So anyway, I'll turn it back on, and then I'll enter the number 10. That was my first number, and then I'll say hit the data button, and it says n equals 1. So in other words, it's telling me it's entered the first piece of data. Then if I go 20 and then hit that button again up here, now it's told me I've entered my second piece of data. And then 30, 40, 50. So I've just entered my 5 pieces of data. The calculator can do a bunch of different things for me. If I want to calculate the average of that X bar is above this bracket, I'd press second bracket, and it tells me the average is 30. When I add up those 5 numbers and divide by 5, yeah, I should get 30. If I forgot how many pieces of data I entered, I'd go second, and then this bracket here, oh yeah, I entered 5. The standard deviation, if this was a sample, the standard deviation, it'll calculate it for me. So I press second and then times button. The standard deviation is 15.8. So that formula we saw, it did all that for me in a click of a button. If those 5 numbers were all of them, the population, then I'd use this one. So 15.8 was the sample, 14.14 is the same calculation. The only difference is the one above the times sign uses n minus 1 on the bottom. The one above the divide sign uses just n on the bottom. And then adding up all the numbers, that would be second plus. Yeah, if I was to add 10, 20, 30, 40, and 50 together, it's 150. If I was to square each of those numbers and add them together, I get 5,500. So my calculator will do all that for me. Your calculator, if it's the same as mine, well, then you could then just use that. If you don't have the same calculator as mine, you can look up your calculator you can look up the manual. If you don't have the manual, which is quite likely, just do a Google search. Mine was the Sharp EL503W, so I typed that in, and you'll easily get web pages that give you the manual. Then you can look up how to do stat functions on your calculator. So it's as easy as that. All right, let's get back to my note. So I can do all that on my calculator, but I don't have to. I can just do it the old-fashioned way with the formulas as well. Here's an example. The ages of participants in a school talent contest are listed below, so there's a whole bunch of numbers here, as you can see. Calculate the mean, the variance, and the standard deviation of the data. Okay, so the first thing we have to decide is this a population or is it a sample? Well, how do I know? So the question is, am I looking at everybody or am I looking at a sample? So is this all the students who are participating in the talent show in this case, or is it some of them and some of them are not being chosen? This seems to indicate that it's all the participants, so I would say this is a case of population. So that lets me decide which formula I'm going to use. All right, if you count up all the different numbers, I think that we found that I'm going to fast track this a little bit. There's 20 pieces of data there. If I want to calculate the mean, then adding all those numbers up adds up to 330. And I could divide that by 20, because that's how we get the mean. That works out to be 16.5. Again, I could have typed all those 20 numbers into my calculator the way I showed you with that other example, and my calculator would have calculated the mean for me as well. The variance would come, again, let me just write over here to remind you, the formula for variance is sigma squared equals sigma, can't draw these, sigma of x squared, so each of those 20 numbers squared and then added together, and then I'd subtract 20 n times the average squared, and I'd divide that by 20. So that's the formula. So putting those actual numbers in, if I was to square each of those numbers and add them all up, that would equal 5,482. And as I said, big N is 20, and we already saw that mu is 16.5, so I would take 16.5 and square that, and I would divide that by 20. Not 20 minus minus 1 because we're dealing with a population. When I do all that, it works out to be 1.85. So that is my variance. Okay. And that is a measure of how spread out the data is. And then if I were to take the square root of that, so I'm just writing sigma again without the squared on it like I had up here. If I take the square root of 1.85, I get 1.36. That's my standard deviation. And again, that is a measure of how far. Think of standard deviation as the average distance each data piece is from the overall average. So take a second to wrap your head around that. It's the average distance each data piece is from the overall average. And so that's my mean. So the average, and these are ages, right? So 16.5 years old. The average distance, the variance is 1.85 years. The standard deviation is 1.36 years. Okay, if I want to plot a histogram of this, I could set it up like this. So we're doing ages on the bottom here, or age on the bottom. So usually if someone is between 14 and 15, we say that they're 14. If someone's between 15 and 16, we say that they're 15. So I could set up the histogram like this, and just again, anyone who's 14 would be in between 14 and 15, and so on. So I set my numbers up here like this. Up here I need frequency on the vertical axis. And 1, 2, 3. So again, I pre-counted these out. There were 2 students who were 14 years old, so the bar would go this high. And there are 3 who are 15. So again, this is just from this list up here. It's just that I've counted these numbers out ahead of time to save us a bit of time. And the highest number was 17-year-olds. There were 6. And then 4 for this group, and 1 person was 19 years old. There is our histogram. Color it in just because I can. All right, so there's my histogram. Oh, and what I should do is I should put this little squiggle here between 0 and 14. That shows them leaving out some numbers. That's just good form. Next part, plot the mean and 1 standard deviation above and below the mean on the histogram. All right, so the mean was 16.5 years. So maybe what I'll do is just use my line here at 16.5. I'll put a line like this. Call that mu, which is 16.5. Now 1 standard deviation, I can just see that at the top of my screen here. 1 standard deviation is 1.36 years. So if I take 16.5 and add 1.36 to that, I get 17.86. So that would be about here on the graph. That's 1 standard deviation above the mean. If I was to take the mean and subtract 1 standard deviation below, then I'll get 15.14. That would be about here. Close enough anyway. All right, so you can see the mean is pretty much in the middle. You can see the standard deviation. You know, between those 2 standard deviations is where it looks like about 2/3 of the data would fall between those 2 standard, the upper and lower 1 standard deviation above or below the mean. So just in case, just so that we have it in our notes, I'll just remind you of what we're doing. So one standard deviation above is mu plus sigma, which equals 16.5 plus 1.36, which is where I got the 17.86 from. And one standard deviation below is mu minus sigma. So same thing, just subtract here. That's where I got 15.14. All right, so that's what standard deviation is. Again, and it's tied into variance. Variance is also a measure of spread. We just don't use it as much. So think of variance as a stepping stone to getting our standard deviation, the one we actually want. The other thing we need to talk about today is something called a Z-score. A Z-score indicates how many standard deviations a data value lies from the mean. That is an important concept. Okay, that should have given me a nice circular shape, but it didn't. There we go. All right, so that is really important term. How many standard deviations a data value lies from the mean? So what we do to get a Z-score is we've got our data set, we've got our mean, we've got our standard deviation. If I pick one piece of data out of a data set, and I want to know where does it fit in the grand scheme of things, I can calculate the Z-score for that. Simple calculation, you just have to know what the different parts stand for. So again, we can do it for population or sample. Actually, the calculation in this case is exactly the same, just with different variables. So let me show you for population. So for the population, X is simply a given data value. So just one number out of a set. And, well, actually, let's look at it for both of these. That's the same for the X over here. Mu is the average, the mean. All right, that was just what we used to represent the mean. And in this case, the mean is represented by X bar. And sigma gives us our standard deviation. Okay, so that's sigma, but that's also what S is. So the exact same formula in each case. Z, again, is how many standard deviations a piece of data is from the mean. So literally, we're taking a piece of data, subtracting the mean, and dividing it by the standard deviation. All right, so let's see how that works. A food manufacturer makes 2-liter jars of pasta sauce. Samples are tested. Samples, that's important to keep in mind, are tested for how close they are to 2 liters. The 2 liters, the jars are filled. 15 samples were taken. Okay, that 15 samples means that that's our little n. Were taken and their volumes in liters were as indicated. So then we have this list of numbers here. So one of the jars was the first one was 2.11, so it was actually slightly more than 2 liters. It was 0.11 liters more than anticipated. But some of them are less, some of them are more. We want to get the sample mean. Again, they even tell us in this case, get the sample mean and the standard deviation. So I could go through, I could use this formula, I could use the formula up here at the top. I could square each of those 15 numbers and then add them together. I could subtract 15 times the average all squared, and I could divide it by 15 minus 1, or 14, and then take the square root of it, get my standard deviation. Or I could just type those 15 numbers in my calculator the way I showed, use those buttons with a few clicks, and that's actually what I did. And again, since I've already showed you how to do that, I'm just going to jump straight to what I got. The average I got was 2.0147, and the standard deviation that I got, which on my calculator was represented by SX. Remember, it's a sample standard deviation, but it popped up to be 0.0 0.072. All right, so the average volume is slightly more than 2 liters. Remember, this is in liters. That's what that's telling me. So of those 15, most of them, or the average was a little bit more than 2 liters. That's good. And the variation, the spread, is 0.072 liters. So if I add or subtract that amount, that's the average distance. They are all from the average. So now we can then use that to calculate the Z-score. So calculate the Z-score of a jar that was filled to a volume of 2.23. So 2.23 is one particular piece of data. That is my value for X. So if I want to get the Z-score now, it's just a matter of taking the formula X minus X bar over S. So X was 2.23 minus X bar 2.015, let's round that up to. Divide that by the standard deviation, 0.072. That works out to 2.99, so almost 3. So in other words, when you think about it, 2.23 liters is very full. And when you compare that to the list of them, that is higher than any other number on the list. Like, that's way up there. It makes sense that what we get is a high Z-score. It's basically telling us that this jar is 3 standard deviations above the mean. So in other words, it's way up there. Calculate the Z-score for a jar that was filled to 1.98 liters. Okay, that's X again, but for a different Z-score. So now it's 1.98. The mean and the standard deviation don't change, so I have the same numbers there. When I work that out, I get negative 0.486. Negative just means that it's below the mean. So this particular, we saw that the mean was 2.015. Obviously 1.98 is less than that, and that's all that the negative is indicating. So this one piece of data was about half a standard deviation less than the average. The manufacturer rejects any jars that are filled to less than 1.5 standard deviations below the mean. Which jars should be rejected? So to understand this, what we're saying is the manufacturer is going to reject any jars that are too empty. They don't want, it's quality control. They don't want to sell a customer a jar that is too empty. And their cutoff, they've decided, is 1.5 standard deviations below the mean. But now we have to figure out what that actually means in terms of volume. So we can do that by taking the Z-score formula and putting 1.5 in for Z, and then we want to figure out what X is. So X is our variable that we're trying to calculate in this case, and it should be, X minus 2.015 over 0.072, and now I'll rearrange to isolate X. So I can multiply both sides by 0.072. I can add 2.15 here. 2.015. Sorry, what have I done? I don't want to add it. I want to subtract that. I know what the problem is. No, I do want to add it. I know what I did here. Sorry. can't stop my recording, so I have to think on the fly. If it's below the mean, 1.5 standard deviations below, then it should have been a negative 1.5. So there we go. I do want to add. I just knew that something funny was going to happen with my answer if I didn't do that. Anyway, so there we go. When I work all that out, I'm going to get 1.907 is x. So anything less than, if we have a jar that is less than 1.907 liters, they're going to reject that. So that's how we can use the z-score. Here's the last thing we need to know for today. I've pre-filled this in a little bit to try and cut down on the length of time a bit. So a normal distribution, as we've already seen, is one that's shaped like a bell curve. It's symmetrical. It's got its highest point in the middle, and it spreads out, tails off to each side. It turns out that a lot of data, if it follows a normal distribution, will always work out proportionally the same way. So what that means is that for a normal distribution, the mean is always in the middle. Okay, so just to highlight something as we go along. So the mean, the average, is always going to be in the middle. It doesn't matter what the specific data is, the average of it will always be in the middle of the curve. And then if I were to add one standard deviation above the average, actually let's keep this like this. If I was to add one standard deviation above the average, for a normal distribution, 34% of the data will always fall between the average and one standard deviation above the average. And since it's symmetrical, it means that 34% of the data will fall between the average and one standard deviation below the average as well. So that's what these symbols at the bottom here are saying. So remember, mu stands for average and sigma stands for standard deviation. So this is just saying average plus one standard deviation. And then this one here is saying average minus one standard deviation. So what we can see for any normal distribution is that 34 plus 34, or 68% of data will always fall within one standard deviation above or below the mean. Now if we were to expand that a little bit and go 2 standard deviations above the mean, well, take a look at this one here. Between one standard deviation, let me do a different color, between one standard deviation above and 2 standard deviations above is always going to be 13.5% of the data. And again, it's symmetrical. So 1 standard deviation, 2 standard deviations below, the difference between those will also be 13.5. If I add all of these 4 segments together, we already know that the ones I've colored yellow are 68%. The ones I've colored green, if I add them together, that's 27%. Adding it all up, that comes to 95%. Well, what's 95%? 95% of data in a set will be between 2 standard deviations below the average and 2 standard deviations above the average. And then finally, again, things tail off on either side. So greater than 2 standard deviations above the average, well, that is 2.35%. Less than 2 standard deviations above the average, but less and greater than 3 below it, is also 2.35%. Add those together, and we get 4.7%. Add that to what we already have, in other words, add that to the 95 we already have, and we get 99.7%. Almost 100%, almost all data in a normal distribution will fall within 3 standard deviations above or below the mean. So we can then use that to make calculations and predictions about things in the future.